All right, in this video, I'm going to continue on with molecular shapes. And again, that could be geometry as well. And in this video, I'm only going to talk about things with, or molecules with 5 things on them. Okay, so everything's going to be 5 things. So first, if we just do 5 atoms and no lone pairs, hopefully you guys remember this one. This is the tricky one, if you remember. We had our central atom, and we had 2 different positions. Remember, the wedge is coming out and the dash is going back. I'm going to highlight this position, and that's the axial position. Those are axial. Remember, it spins on the axis like a wheel would. And then I can highlight these other 3. Those, if you remember, are the equatorial positions. Okay, and the axial and equatorial are all 90 degrees from each other. And then the equatorial positions are all 120 degrees from each other. And hopefully you remember what this is called. This is trigonal bipyramidal. And so an example of that would be PCl5. So we have chlorine, chlorine. Now we just have 5 chlorines on here. And we got to distribute all the chlorines. It's important that you put these lone pairs out here because otherwise you don't know when you have the correct Lewis structure drawn. Because you have to ask yourself if you've used all your chlorine or all your all of your electrons. Sorry, I didn't like that phosphorus. There we go. Anyway, PCl5 is a trigonal bipyramidal molecule. Now, when you draw this on paper, just remember it's going to look probably more like this. I'm not going to draw the lone pairs just for this. It'll probably look something like that, and you think it's all planar, but it's not. You're just drawing it on a piece of paper, okay? All right, we're going to add a lone pair. So we're going to have 4 atoms plus 1 lone pair. And that's still, again, 5 things. I'm going to stop writing that again, too. 5 things. All right, now, the important thing here is because this is valence shell electron pair repulsion theory, the VSEPR theory, the molecule is trying to minimize repulsive forces. So when we put the lone pair in to this basic trigonal bipyramidal shape, it matters where it goes. And the reason it matters is because we want that lone pair to be as far away from everything else as possible. So the 2 axial positions are actually 90 degrees from 3 other atoms, but the equatorial positions are 90 degrees from 2, but 120 degrees from the other 2 equatorial. So lone pairs always go equatorial. Okay, remember that. Let's just write that down. Lone pairs, lone electron pairs go in equatorial positions. Okay, that is important for you to remember on an exam. Okay, so let's look at this guy. And we have an atom. I'm going to put the lone pair right here. And it's, I could have put it in any of these equatorial positions, but some of it's just so it's easier for me to draw. Okay, and it's really difficult to see in this drawing, but if I had these two equatorial positions kind of sitting on a bench top, one of the axial atoms would land on the bench top and then it would rock back to the other one, and it looks an awful lot like a seesaw. And that is the name of this shape, seesaw. And let's talk about a molecule, just an example, SF4. Okay, SF4 is that seesaw shape. Okay, let's add one more lone pair. So we'll have 3 atoms and 2 lone pairs. 3 atoms and 2 lone pairs this time. And still goes in that equatorial position, that lone pair. So this time I'm going to kind of change where I put those lone pairs. I'm going to put them in these positions here. Yeah, those are the lone pairs. And the only reason is it makes it easier to see what why this shape gets its name. This shape is very simply T-shaped. Okay. And an example of this, of a T-shaped molecule, would be ClF3. Cl. And you don't necessarily have to put those electrons in the wedges and the dots. You could just leave them right on that central atom. But again, you got to go back and think, okay, there's 5 things around the central atom. 2 of them are lone pairs, so that means this is a T-shaped molecule. And one final one. We have 2 atoms plus 3 lone pairs. Okay, 2 atoms, 3 lone pairs. Again, the electrons go in the equatorial positions. So these are all going to be, and I'm not going to ask you to draw structures like this. Don't worry about exactly the way I'm drawing it. I'm trying to depict it as best I can in terms of the actual geometry, but I don't ask you guys to draw them like that. Okay, and I think you can see what this shape is going to be called. It's just simply linear. But notice it's a different linear than the one with just 2 atoms. Okay, and an example of a linear molecule would be xenon difluoride. So xenon there, fluorine, fluorine. Now xenon does not normally react, but we can force it to react. And it will react with fluorine because it's the most electronegative element. So we can force it to react. So there's an example of a linear molecule.